do some Michael Jackson stuff.
I think so.
Yeah.
Yeah, no one's
So it's just, did you find it right here?
You mean with the microphone?
The microphone?
Yeah, just I think because this.
Do we know? Oh, and Bianca.
We're gonna have.
You need at least 30. You need 30 of them to get to the same volume.
I don't care about 30. I just want to increase my time. If you can do it for 10 hours, I can do it for 30 hours, and I don't give a shit. I can go bowling.
No. If I do it for 10 hours, if you only have one of them, you need to do it 30 times as long.
But no, if I have this, if I have that, if you can mask those.
Yeah.
But you can't. So I haven't talked about the data analysis anymore. You need to identify every single diamond that's in the instant feed and then collect for it. You cannot mess everything else because it's a high feed.
Sorry, as chair, I'm cutting off this conversation. Students be down there. Because you have to the PowerPoint's not selected. What do you want? You have to select on the screen. You what is your microphone? Yeah. Okay, everybody. We have to get to lunch at some point, so let's get going. I know everyone's excited. Everyone's excited. Pressure is an exciting topic. Are you chastising us? Or it's the coffee? I don't know. Starbucks a little stronger than the coffee yesterday. Anyways, Stan Tozer, please go ahead. Thank you very much.
Yes. Whoa. Is that good?
You might want to move the microphone.
I'm thinking so. Because, as it was pointed out to Nick and myself, we have really big voices. So. In other words, we like to yak. Anyway, as you see, the high pressure community is very vocal, and we love to disagree with each other and tell each other why we're wrong, or the other person's wrong while we're right. And all of this is typically resolved not in the media, and God forbid, not in PubPeer or PeerPub, but just over a beer or something at the Gordon Conference. So one thing I would absolutely suggest to you is that you check out the Gordon Conference on high pressure research. It's used to be at Kimball Union Academy, which was awesome because you got to dive in to this creek off of this bluff, and you scared the shit out of yourself because there are big ass boulders below. But it was a great experience to do it. Right now it's at Holderness, which is good fun, but you get to go swim out in Squam Lake and all that good stuff. But the afternoon conversations are fantastic. I don't know if you've been to a Gordon conference or not, but mornings are presentations, and then the afternoon you have yourself, and you get to go play, and then you get back for the evening sessions, and it's crazy intense like this, but you get huge exposure to a lot of people that do just high pressure, and it is a very quirky field of research. So I would strongly advise that you look into that. Okay, so now I'm going to take what Adam did and what Bianca didn't do, which is dare, and we're going to totally throw away all of what Adam suggested, which is really good, and it has its place, and it's the way that I did high pressure research for years until I jumped into the superhydrides, at which point I realized that I had to abandon all of the good think, throw it out, and just live with all of the ugliness of working at 2 megabar pressure. It's non-hydrostatic, it's not homogeneous growth, but you get to do some really cool stuff too. So there are all these trade-offs, right? Adam used the word choice. Choice is a very nice word. I like that word. I was trying to think, trade-offs always sound like you're chucking something away. Choice sounds like, oh, I've decided that I want to take this aspect of the problem, right, and deal with it. It's like when you write your proposals, they tell you never to use the word problem or issue. It's a challenge, right? So remember that when you're writing your proposals, it's always the challenges that you want to address in your proposal. And it's not the issues or the problems, because they don't want to hear that kind of thing, right? So, what I will first talk about is what Ryan Baumbach also discussed, is, what's the science that you want to do, and is high pressure necessary? Because high pressure is a Pandora's box. It will walk you out into this infinite phase space, and as Adam pointed out, you got to really pay attention to all the details of what you're doing. Otherwise, you could be looking at the schmutz effect. I love the fact that you use schmutz, because in my lab, it is a sacrosanct word. Schmutz, defines many things, right? And often the result that you have. so you need to be careful of that. But it really plays well with unconventional versus BCS, reentrant superconductivity, as the folks here are doing. Superconductivity, the same thing. For us, it was the competing orders that we wanted to look at for YBCO, the COOP rates. We've also toyed with it a bit with the FFLO state, which we worked on a long time ago, 2001, 2002. Metallic hydrogen is all over the place, right? You've got to have pressure. And now with the superhydrides, unless, of course, you believe lutetium hydride needs big pressures, right? So the cool thing about it is that it can almost continuously and smoothly tune energy states. But if a high pressure scientist tells you that, he's smoking some good stuff, or she, because that's not the case. But it's a reasonably clean way to tune energy states, and that's what you're getting at when you're using pressure, right? You're changing angles, changing bond lengths, overlap, et cetera, that Adam had pointed out. But the other thing you're doing is you're suppressing orders, competing orders. You're inducing superconductivity in some cases, or other phenomena that you want to study. And then there are all sorts of crazy things that you want to get at, as far as what I want to study in order to address these scientific issues. Okay, but it gets a little bit messy too. Okay, especially high pressure growth. I use trade-offs. Sorry, choices. We'll stick with choices. I like that word better. I'm going to change it. But in doing high field research at high pressure, low temperatures or high temperatures, there are always trade-offs, right? For the DC magnets, I just figure out what time I started. Okay, for the DC magnets, it's the trade-off. Oops, sorry. Going back there. The trade-off is that with a hybrid magnet that we have at the magnet lab, you have a superconducting magnet, resistive magnet inside it. You're limited to starting out at 14 Tesla and then going up to 45. Resistive magnets, we can go 0 to 35. And then this way cool magnet that we just used the heck out of when we were looking at the superhydride, 0 to 42 Tesla up and down all day long, especially when it's the pandemic, which seems to be a common theme these days, right? We had the magnet to ourselves. We weren't accepting users, and Audrey and I just camped down at cell 6 and used it until Tim finally kicked us out and said, you guys are going home, you're gonna kill one of us because you're gonna come in with COVID, and you're gonna spread it all over the lab. But we were just having so much freaking fun. It was just great, right? So it's a fantastic facility. If you haven't used the National High Magnetic Field Lab and you need big magnets and really good people to help you get the data, it's a great place to go, okay? So I strongly encourage you to look at that. There is also the possibility of doing pulse field experiments, and for the superhydrides and for the study on the COOP rates that I'll talk about very, very briefly, we needed those higher fields because we wanted to push through the superconducting dome, go to the other side of the superconducting dome, and look at how the Fermi surface of that material had evolved. Okay, the disadvantage with pulse fields, or the choice that you make with pulse fields, is that you have a very limited amount of time. Here I've got gobs of time, as much time as I want, as much time as they'll give me, as much energy as they'll give me. During the course of an 8-hour shift, I can mess around with field up, down, get really clean data, go look at a particular bit of field space, whereas here, you blink and your experiment's over. You need super sophisticated guys and gals that have done this kind of work blowing shit up, right? Because that's what Los Alamos does. And therefore, they have the people there that can take data, really, really good data in milliseconds or microseconds of time. It is the most important aspect of any high field facility, any X-ray field or neutron facility are the folks that man it, because they're the ones that want those experiments to work, not only yours, but theirs. And so they take the time to get it right. Okay? And at the Mag Lab, they've done just that. And it's not just at our facility, but also at the facility in Dresden, where we go often, and also in Grenoble, and Toulouse, and Wuhan in China, and in Japan at ISSP, where they have this crazy cool 1,000 Tesla magnet up and down in a microsecond or 3 microseconds of time, but can get some really cool data. Okay. So these are all the trade-offs or choices. The blue choices are good. You get lots and lots of time in pulse magnetic fields. You can get multiple weeks of time in resistive magnets. You get 1 to 3 weeks per year. And the downside of it is that for us, because we come with all of our equipment, we come with probes, we come with our diamond cells, and we come with our cryostats when we go to a pulse magnet. The only thing that we use are their magnets and their data acquisition. And the electronics are all developed by this guru that we had in the group, William Caniglio. Okay, so these are all the various things that you have to take into account. If you want to do really low temperatures, you've got to come to a DC facility. About the best that we can do in pulse magnets is about 400 milli-K, a little bit lower. Okay, and then the other big trade-off in pulse magnets, the bores typically are smaller than that which you'll find in the DC magnets. Okay, but you can make really small diamond cells, so that's not an issue. Right? And you can make small diamond cells to get to megabar pressure and do transport measurements and all that good stuff. And that's what I'm going to talk about today. Okay?
Can you just comment on the very last line? I just noticed that.
Probably one of the most important aspects of pulse labs is that if you go to Los Alamos, you can get the best gosh darn burrito that you will ever have in your entire life. And I'm happy to share that information with you, although it is, pretty secret. There's a guy in a little shack that's down there in White Rock that has the bomb for the burrito, right? And we always stay in White Rock because we could go right off the edge of the rim and do our morning walk down to the river and back up, and by the time you get up, you've been accosted by at least one mountain lion, and you feel, life's good. I love Los Alamos; it's a fantastic place, right? And then I shouldn't leave out the duck, because the cassoulet in Toulouse is, it's just the best, right? And regionally in Europe, they do all of, every region within France, every region within Germany has a particular food that they're really good at doing. Dresden has some fantastic yummies, and France, well, enough said. Right? It's just fantastic food. And if you come to Tallahassee, I can tell you where to get some really good cheese grits. So, not my favorite, but every place has its own thing that it brings to it. So those are really positive on, food's positive no matter where you go. Scenery and hiking and all the other things that come with going to these various facilities, that's always a plus side. So, thanks for pointing that out. Didn't want to miss that. So, this is where the timeline for, and I'm going to focus on superconductivity, right? I'm going to talk about the Coop rates for an example leading into just how we do some measurements. And then I'm going to jump right in and dial it up to 11 and talk about the superhydrides, okay? But this was a landscape up until, about 2015. We were, people had looked at the elemental and the binaries, and then, along came the Coop rates in 1986. It really changed the landscape for superconductivity. And, you know, quickly, I mean, that was amazing. If you ever get a chance, go online and look at the 1987 New York, the Woodstock, right? It's great. The energy in that room that evening when they discussed the initial results is just phenomenal. Everybody walked out of that conference, one, sweaty as hell because it was so crowded, but people were just juiced, right? They were so excited about this. And within a very, very short period of time, Paul Chu had bumped the transition temperature from 39 Kelvin to 93, right? He did it because of intuition, looking at how pressure had changed the properties of the lanthanum analog that, you know, that they had worked on, that, you know, was the first cuprate to come out, right? So pressure is there in the cuprates right away, but not for synthesis, but for just looking at how TC was moved. In fact, for the mercury compound, pressure 330 GPa pops it up to about 157 Kelvin. We're doing pretty well at that point, right? But it's, and it's also, you know, the rise is pretty stiff here, right? And then you've got, you know, you've got the MgP2, you've got the iron arsenides, all beautiful classes of the superconductors, but I'm not going to focus there. Oh, I'll get the button right. Yeah. What we wanted to do is to look at this phase diagram of the cuprates, and in particular YBCO. It's just a favorite. I worked on it when I was as a postdoc at IBM, and then, you know, the group got together and they really wanted to have a look at, you know, could we use pressure, you know, starting out at 0.11 for the doping, and drive it with pressure, drive through that or across that phase space over the superconducting dome, because there are lots of theories out there about, you know, the Fermi surface is going to reconstruct when you go across the superconducting dome. All sorts of crazy stuff's going to happen. High-Fair has some really good stuff going on with doping, but we wanted to use pressure in order to do that, right? And so this is one of the initial, I'll say initial, right? It took a bucket load of work to get here. This is a pulse field experiment at Dresden's pulse field facility, right, on YBCO. It's just, you know, it's a 0.8 GPa, 500 millikelvin. Again, this is all stuff that we've put together, that even the pumping stations, we were the ones that were telling them, buy this, don't buy that. So to get down to these reasonably low temperatures, the diamond cell's plastic, the gasket's plastic. Somebody was asking about it, is there something else other than metal that you can use? Yeah, there's a plastic that you can use, or fiber that you can use, and then make your cubic boron nitride insert to have a fully non-metallic diamond anvil cell. And we wanted that for these pulse field studies, right? And we're using this technique, you might have heard of it, tunnel diode oscillator, or you might more often, it's the proximity detector. It's a metal detector, right? That you sit there and scoot around and find all those lovely coins over in Europe. But we use it to detect the TC, HC, and quantum oscillations, because we wanted to look at the Fermi surface of this material. So here we're popping through HC, and then we get these beautiful quantum oscillations. These are up and down sweeps. So the data, and we don't see, you know, negligible heating. I would say zero heating. I think it's just offset from vibrations at this point. This is a 72 Tesla magnet. You know, we take it comfortably up to 65 and back down, because we want to do multiple experiments. We've blown up 3 of their magnets so far, and we're still welcome back. But the data is crazy clean for pulse magnet, right? They have done an exceptional job in making these large bore, very slow rise pulse magnets so that you can get really clean data. Okay? And I should point out, with most of our stuff, we try to present the raw data just so that people can, you know, take it, use it, and tell us that we're wrong. So this is data, same material, but now we're starting to scoot up in pressure rather rapidly. We could, with the pulse magnet, get up to about 6 to 6.8 GPa before we bumped up against the superconducting dome. And at that point, your HC is rising to the point where we can't see quantum oscillations any further. So we went into the DC magnet, the hybrid magnet, where we could do some measurements up to about 6 or so, or 60 kilobar, 6 GPa, and then we lose. There are no quantum. This is 6.8 or so. We no longer can see the quantum oscillations, which we see here, right? But then once we push through, we can actually see at 25 GPa. Here's the trace, right? The blue trace up top. But if you blow that up, you see quantum oscillations, right? Now, they're pretty ugly, they're pretty noisy, but they are quantum oscillations. Here's the setup for that system, looking through the through the diamonds, and through that, in this case, a diamond powder epoxy mixture, because it's much stiffer. And this is the coil that Audrey's wound. Here's a sample of YBCO. You can see just along the top of the rim here, some ruby crystal, okay? And this is the first time quantum oscillations have been seen anywhere near this pressure. In fact, anything above. Audrey owns it from 10 GPa and above. She's the one that's gotten quantum oscillations in the nickel disulfide with molten Roche and a couple other systems in the YPCO. So, and then to verify that those are indeed quantum oscillations, what we did was a temperature-dependent study, right? And that's what we have here, right? So you've got your lowest temperature, right? We reproduce, we see, and these are just offset for clarity. Okay, and then you can see as you pop up through and eventually get to 5 Kelvin, that the quantum oscillations disappear, just as one would expect for the system. Yeah.
So I'm just trying to understand, where are we in the phase diagram?
Yeah, so let's back out. Sorry.
6.5 is under doped, right?
So, yeah, so we start out here at 0.11, right? And we push up to the point where we can no longer, because HC is growing to the point. And then we have definitely pushed through and over because our TCs come down. We measure our TC separately because when you're running magnets, you only get so much time. Or the DC magnets or the pulse magnet, and a lot of times when you're lowering the cell, you can't get a good temperature cool down, and so your TC stinks, right? So instead we run it in the PPMS. There's a disadvantage that we'll own. Every single time you cool a pressure cell, it changes the pressure just a little bit, right? So you have to cool your pressure cell down multiple times before you do the measurement, so that you're reasonably stable, and then you do these measurements, quantum oscillation measurements, and then you also measure the pressure in the cell with a PPMS.
TC at 25?
What's that?
What's the TC?
Forgotten, top of my head. We have it in, the manuscript is finally out after 6 years. We've got it at PRL, and hopefully they won't laugh and they'll send it out for review. We'll see. Yeah, I've forgotten what it is. So I've got the data on that. I can show you. Okay. All right. So now what we're going to do, that's what you can do. Yep, you're going to have to speak up. I can tell you one thing also that I come away with is that I've had multiple magnets blow up in my ears, and it's about a stick of TNT, and my hearing in one of my ears isn't so great anymore. So, and I had one that actually land behind me, and that was probably more scary than the explosion. So. Yeah, the quantum oscillations. What do you want to know?
How it could be like field fluctuation? Like how do you say that?
Well, how do we know that they're quantum oscillation? Yeah. Because they die off with temperature. So, and we could actually map them out, and people have done also studies with YBCO on cantilevers and also in coils at ambient pressure, and we can map our frequencies onto that known frequency at ambient. But you want to know whether it could be some type of other phenomena?
Maybe field fluctuations.
It could be. I would not think that would be what you would see if you had a spin fluctuation. Yeah. We can talk about it. Yeah. So now I've given you a flavor for what you can do in high magnetic fields with very, very small diamond amyl cells. These diamond amyl cells that we used for those two studies, the plastic cell is 9.5 millimeter in diameter and 11 millimeter tall, right? And the metal version of that cell that got us up to higher pressures is 11.5 millimeter diameter and 14 millimeter tall. It's a turnbuckle design that I'll discuss in a little bit.
Just really quickly, are those custom plastic cells that you built?
Yeah, it's a plastic, unfortunately, it's no longer made. And that has a history. It takes about an hour to discuss, but I'm happy to tell you about that too. Katrina wiped it out, unfortunately, and it's never come back. And it doesn't appear that it ever will come back. So again, here's this landscape of superconductivity, right, up to about 2015, and then Ermetz comes up with this amazing finding. I don't know why that's way the heck over there. It's supposed to be there at 2015. I'll change my dot. 203 Kelvin, right? This was crazy. The Ermetz is a monster. I mean, the people in his group, he told his people when he discovered this, you know, there are so many fun things in the high pressure community, right? When they found this, he told all of the people in his group to send their families home to Russia, that they would not be seeing them anymore until they had this result in hand, right? The guy, I mean, he works his group hard. He works harder, twice as hard as the people in his group. He never, ever gives up. And there are some tales that I can tell about Mukhtar and Ermetz that aren't for the public audience, but over a beer, yeah, we can talk about him. He's a monster, and in a good way. He loves high pressure. This guy's crazy. Oh, but where we started out was, you know, after they'd come up with that, and then Zulu and Mukhtar had come up with lanthanum hydrogen 10. They were in Russ Hemley's group, right? And then Ermetz heard about this at a conference where Russ presented prior to publication, Big Boo Boo. And Ermetz's guys also reproduced the lanthanum hydride, right? We thought, you know, we're going to use high fields and see what we can see in high fields with lanthanum hydride. We had all of this knowledge about how to make small diamond cells, how to do quantum oscillation measurements, TC, all this other crazy stuff in the field. What we needed was a new diamond cell that gets to these crazy high pressures, and we needed to forgive ourselves for throwing away all the things that I've taught the group about hydrostatic conditions and doing everything just so, and just, you know, hammering your sample, right? And that's where we came into this, not knowing that success rate is 1 in 7 for these measurements, and every single time you take a diamond cell up above 1.1 megabar, would you say that's about the number that you have as well? The diamonds, most of the diamonds fail. They either fail catastrophically, or they fail with ring cracks, or if you have a successful experiment and you don't coat your diamonds, eventually the hydrogen diffuses through into the diamonds and the diamonds crack as well. And that's actually what we have here. Here is what used to be this beautiful diamond, right, with electrodes on it and all this good kind of stuff. And after a year and a half, actually a year and 8 months time, the hydrogen diffused in and you have this beautiful salt pillar of diamond, and your experiment's over, unfortunately, because this was the cell in which we saw what we believe to be a crazy high TC superconductor, 550 Kelvin onset, very broad, as one would expect. Our TC doesn't have a width of 1 Kelvin, and God forbid that it should at room temperature, because then we've found a way to get around phonons, and that's just not the case, right? So it's ugly, and we own it, but it's a pretty cool result. And then we have reproduced, and we're trying to move forward with devices at this point. And that's what I'm going to talk about for the rest of it, is how do you get there, right? But the synthesis of the superhydrides is messy, right? You put in a piece, in this case, it was hydrogen disulfide. You put it into your diamond cells. Ermetz's postdoc hated it because it's the molecule that you put into gas that stinks to high heaven, so that you know you've got a leak in your gas line. right? He was loading this stuff all the time, and he just hated life. But he was getting some great results. You know, it was super crazy good, throws off, crazy good throws off, right? But you could see it. I mean, it doesn't look like a superconductor, right? You got it. You're coming up. You're going down. You do a couple of cycles with this thing. Here's the history of it, right? And all of a sudden you see a transition here, which is actually a good tell, right? That's exactly where you expect superconducting sulfur at these pressures, right? Good, just like in a high pressure cell, where you use gold, platinum, palladium, whatever as a calibrant. Here's your calibrant, right? Yeah, so we know exactly what the pressure dependence of the TC for sulfur is, and we can tell that, you know, it confirms this 143, right? Do a couple more, you've got non-zero, you know, same system. You're just going through thermal cycles at this point. All of a sudden you've got this a non-zero resistance, not something that is unexpected for this environment in which you're growing material, okay? And then eventually, after you've cycled through several times, gosh darn, you have this beautiful family of curves, right? Interestingly enough, you know, the value here is coming down dramatically as you go further up with more cycles and go out in pressure. That's not something you always see, okay? But this was a finding that just turned this field on its head, right? And had people, it was in the media, it was just everywhere. And there are only a few groups in the world that can do it, unfortunately, because of the pressure range. And that's one of the damning things for this field, is that not enough people are in it that can confirm the data so that, you know, we can keep ourselves honest, right? Now, what Audrey and I and William really wanted to do was a multi-probe approach to this synthesis, because every single time you grow a superhydride, it grows differently. You're taking a material, sulfur or hydrogen disulfide, or lanthanum in our case. You're sticking a little flake of it into your gasket, right? You're mashing it with either hydrogen in there or ammonium borate, which is a hydrogen source, or wax, which is also another hydrogen source. And then you're using a laser and you're just smacking the living daylights out of this thing, right? And you're doing it multiple times. But the problem is that your laser spot is crazy small. Your sample's small. It's only, you know, 20 microns in diameter, 1 micron to 2 microns thick. And you're rastering across your sample. So you come up, you smack it a couple times in one spot, you get a white flash, you're at the X-ray facility, you see this nice white flash, and you've coupled to your hydrogen source, and that you can see the evolution because your sample typically grows in size as it pulls in the hydrogen. All of this was based on theoretical calculation, or a theory that Neil Ashcroft put forward first in 68 on metallic hydrogen. Eventually, he realized that experimentalists just couldn't get their stuff together. And so he said, hey, how about, you know, using a host metal and we'll just stuff hydrogen into it. And that's what started this whole experimental race where Airmets was at the lead along with Russ Hemley and his group. Okay, and then in addition to the laser heating, you know, we want to be able to do optical diagnostics, X-ray, Raman, that type of thing, and we want to be able to do transport measurements. So resistance versus temperature, and then eventually, you know, what we really hope is to be able to do our quantum oscillations. But there, you need typically an extremely hydrostatic environment, extremely clean crystals, all the things that we don't have right now with the superhydride, but that's where we want to push in the end. The other thing that we want to do are look at devices, and that's what this is here. These gold lines are the electrical leads coming in to give you a reference. This circle here, that's the QLIT. It's 65 micron in diameter. The sample that you see here in blue is a ring that's 17 micron OD, about 12 micron-ish ID, and the sample is, in this case, it was 2 micron thick, okay? They're really small, but the cool thing is this allows us to start thinking about flux gates, okay? I can take that ring, I can slice it in half, I can add in, oh, sorry, I should point out that all of this is done with FIB. I don't know if who's familiar with FIB? Yeah, okay. So when people ask me what the heck FIB is, focused ion beam, I say I'm tagging to make electrodes and samples, et cetera, right? It's spray painting, but a really glorified spray painter. And the machines are just, it's really amazing what you can do now with, making samples, defining electrodes. The devices you can do are just beautiful, okay? So what we want to be able to do is, make a flux gate, and we have multiple taps here to try to do resistance too on the same sample. But if we can see flux, quantized flux, boom, we're golden at this point, right? Even at this pressure, we have something that we can start thinking about quantum information. Right? It's not going to last long, but because the hydrogen is eventually going to seep into the stone and game's over. And then on top of that, what we have is a susceptibility, just a single turn coil with a toroid ring here that we've cut into it with the FIB, and our compensation coil out here. So what we want to be able to do is also like a TDO measurement or a TDR measurement, time domain reflectometry, where we can look for superconductivity. Okay? But we want to be able to do all of this in one sample because we have sample variation big time. Our sample, we're essentially, so I was talking to Nick and JP about this, and we're trying to come up with an analogy to crystal growth that Ryan Baumbach talked about, right? Where he's got a crucible and he sits, puts his crucible in at a fixed temperature, or venton, fixed temperature, fixed amount of time, long time, and then you cool it down in a very controlled fashion, and you spin off the flux, and you're left with, you hope, gorgeous crystals. And at that point, still, you select through your crystals, and you go, no, oh, here's a beautiful one. It gives me exactly, what I hope, superconductivity at, who knows what temperature, quantum oscillations out the yin-yang, because the crystals that you can grow in this environment they're just beautiful, right? Super clean crystals. We don't have that. We are measuring our entire crucible, right? We have a slab of lanthanum that we hope, well, now we know, is well defined because we're defining our sample with FIB. So we can define it very carefully. We can anchor it to our electrodes so it doesn't slip around. I'll show you our initial result where the sample of lanthanum was too big, too thick. It shot out the side of the anvil, but still enough in contact with electrodes so that we could do these measurements, right? When you're measuring the crucible and our heating, which I'll show you in a little bit, gives you this crazy inhomogeneous growth, lots of off-stoichiometric materials, and then this fleck, in our case, of what we wanted to, not what we wanted. This was absolutely serendipitous. As Ryan pointed out, a lot of times it's just serendipitous discovery. And in this case, it was as well. Okay? So, laundry list, I put it in there so if you look at the talks later, you can have it. But just on the various issues, much like Adam talked about, but now all the nice things that Adam tells you to do correctly, we sort of throw out and do it differently. These are just some pictures of conventional. This is Audrey's setup for doing TDO up to 25 GPa with a wire. This is a 10 micron copper wire. I think it's 2-turn at this point, and bringing the wire back out. Here's the resistivity setup where I've made contacts to a crystal so we can do Hall measurements across here and also do some resistance measurements. And then here it's where it's all jacked up on steroids with FIB, right? This is what Tony Helm did in a study on cerium, rhodium, indium-5, one of these 115 heavy fermion systems. This is a 600 micron culet, just so you have a, because we didn't think it was going to work. So we started out with big culets. This is Tony's device, right? Here is his little crystal of cerium, rhodium, indium-5, which he's thinned down to a couple microns. And then he's cut in so that he has, and added in these electrodes, you can see here. And then these bridges to the sample so that he can measure resistance along here, and then also orthogonally to that at high pressures in a pulse magnet using this plastic diamond cell with the plastic gasket. Okay, but the other things you can do, we have this TDO coil. right? We've, just in screwing around, we've come up with this method to make this coil, right? Now you say, how the heck do you get out to your other lead so you can do that? That we cut a hole in our sample and bring that center tap out, and then we bridge to that with another lead that's on the upper stem. It hasn't worked yet, but it's going to. We're pretty confident. So, but there are just all sorts of cool things that you can do with FIB that you can do conventionally, but now with FIB you can go to higher pressures. So it's pretty cool. All right. So some of the rules. I didn't want to leave out Jim. He's one of the guys that used to go to the Gordon conference, and he would give a talk with massively inappropriate jokes, which we would never tell nor want to tell in the more aware environment that we live in. But back then, you know, science was, you know, it's not what it is today. It wasn't as welcoming to the community, and now I think it's much improved. Okay, but this guy, you could ask him any questions. He's like Bianca. If I have a question, I go to Bianca because she's an encyclopedia, right? And she knows not only all the good folklore, but she also knows all the cool stuff. And if she doesn't know, we can go to Reini, and Reini will be able to tell us exactly how to do it too. And Jim was of this, you know, the same, you know, mindset. He knew either how to do it or the person to ask, so that you can get it done, right? There are some you know, there are crazy rules in high pressure research, right? Somebody was asking about gasket ratios. Our golden rule is 10 to 3 to 1, right? So your culet is 10, your hole is, you know, a third that, and the thickness of your gasket is a tenth of that, right? Usually you can get to reasonable pressures, 20 GPa if you follow that rule. There are just all sorts of things that these guys could tell you. Aramets being another one, Stishoff being another one, right? So I mentioned this nickel chrome aluminum, right? Trying to get nickel chrome aluminum out of Russia was really, really difficult. I had this beautiful letter. The director of the lab, Jack Crow, took it because he called us imperialist dogs, and then he would not give us this nickel chrome aluminum, which eventually the Japanese reverse engineered, Matsumoto, and now we have it. But it is amazing, all the little stories that you can pick up from folks, and in those stories there are lots of good little nuggets about how to do experiments correctly. You know, challenge the norm, crash and burn, please, often, quickly, and then learn from your mistakes and move forward and forgive yourself, right? Because that's how you're going to get the data that you want, right? And you know, energy scales matter. Not only in what level of pressure is necessary to get to the interesting physics. If you're in you're doing biology, 2 kilobar and you're just doing some crazy good science, right? You know, you need a little bit more to look at the heavy fermion systems, and you need ridiculous pressures for the superhydrogens, and metallic hydrogen is just way up there, right? But people are getting there either statically or dynamically, right? And I didn't want to leave out Percy because there's also a lesson here with Percy, in that people will tell you just about everything you need to know about high pressure, but Percy conveniently left out his mushroom seal. He never shared that with anybody. He was very welcoming. People come to his lab, they would sit and chat forever. He would share drawings with them, everything but the mushroom seal. And the mushroom seal was the one critical thing that allowed him to get to crazy high pressures. And talk about a person who just published, he was a prolific publisher of beautiful experimental data. So, but Percy also was a bit driven, and you know, here's a picture of the bomb. The bomb blew up one time, and it killed his technician. Okay, so high pressure, you need to worry about energy scales, and you need to worry about other people in the room, and you need to take the time. You know, it's that 2-second rule. Take the time to think about what you're doing, and if you could do it more safely, and talk with your buddies, and maybe they've got some good ideas about what you forgot. Okay.
Stan?
Yeah.
Since the Bridgman cell hasn't been shown, can you just say 30 seconds about how that works?
I could if I were informed enough to. I've only used a Bridgman cell once in my life, and so I would not be the appropriate person to discuss it. however, I mean, it's just beautiful, you know, setup with these anvils with sometimes toroids developed on top. Big samples. You can do. You've used it. Yes. Okay. Here we go.
The Bowler cell is the briny cell is effectively the Bridgman cell. Like the actual heart of the Bridgman cell is a clamp and then retaining rings, and it has similar tapered shapes. So that kind of tapered anvil that you would have in some of the diamond cells that you use in neutrons harkens back to this. Most of the time, these were tungsten carbide. Occasionally, after Bridgman, they became sintered diamond. But I don't think Bridgman ever used sintered diamond.
Right, and I had, so that's the other nice thing back in the day, right? I had, they were working with ceramics at Ford, and there was a guy at Ford, Bob, I forget his name, 30 years ago, right? Who made a set of the anvils for me, just out of the Ceramet that they had developed, right? And sent them to me for free. Right? It's crazy the things that people will do for you. All right, and Bianca also had mentioned the MBS and the whole thing of the diamond cells and how they came about. I find it really cool that, yes, they had access to like just bucket loads of diamonds, right? The drawers they would talk about, that they pull out and just say, yes, that, right? It was like, you know, going to Walmart, but actually cool shit. So the diamonds that they were allowed to take were amazing, and the get up that they used, they took a diamond and they drilled a hole through it painstakingly, right? And then they stuck in pistons from either end and tried to do the measurement. Well, they learned something very quickly about diamond. It is great in compression and it stinks in tension, right? Snap the diamond. Well, what do? You go back and get a bigger diamond, right? And that's what they did. They got a 7.5 carat diamond and repeated the result. So don't use diamonds in tension. It's not a good thing, right? So, but these guys were just, you know, it was amazing what they could do with diamond anvil cells early on. It was all optical at that point in the 50s, but cool stuff. You can learn some good stuff by going back into the literature. Okay, this is that stupid slide. Okay, Adam's already talked about this. I'm not going to go into it, but and he's talked about mechanisms and all this stuff. So I think you can pass on that. And Bianca mentioned this. People ask me about talking, you know, how does what is a diamond cell? It's a nutcracker, right? You've got your diamonds, those are the jaws of your nutcracker, and you've got your mechanism, that's the handle on the back side. And you know, what we don't have with a nutcracker is alignment, but I can crack a nut, and that's pretty much what I'm doing in a diamond cell too, right? But that's when you're really, you know, taking it down a level so you can talk to the public when they come to your science day, your lab. What we have, and interesting enough, folks that do high pressure often do, you know, use pretty unique cells and design their own cells, and that's what we did. This cell design that I came up with based on a turnbuckle was something that came to me when I was walking with Dieter Hochheimer in Colorado after a conference, after an ARAC conference actually, and we were walking through this beautiful field, you know, flowers and all that kind of stuff, right? And there's this high tension line with this cable coming, you know, down with a turnbuckle, you know, to draw it, put it under tension to keep it steady, right? And I look at that thing and I'm like, holy crap, I could use that, you know, in the reverse direction, put my diamonds on the inside of the turnbuckle, crank the turnbuckle body, and boom, I've got a diamond anvil cell with a minimal number of parts. You know, let's say, opposed to the gasket and the diamonds, which every cell has, I've got 3 parts. I have a left-hand end cap, a right-hand end cap, my diamonds on those, and the body that turns, and it brings the 2 diamonds together as long as you hold them fixed, and you can generate crazy high pressure stories, right? And it's super compact. And you throw away all of the proper thinking about how to design a diamond cell, alignment and all this crazy stuff, and you count on your machinist designing, or you design, they make a super precise diamond cell where the cups that the diamond sits in and also aligned to the body of the cell are super precise, and then your cutter and polisher of the diamonds has to do a really good job with concentricity of the girdle of the stone to the tip of the stone. So but that's what that is here, right here. Left hand, right hand, diamond sits in here or sits up in there, holes through for electrical leads, all that good kind of stuff. And the concept is just that we've taken diamonds, put it on the ends of these two screws, left and right hand screws. Here's the body, and you just turn that, which is the green here, boom, you've got a pressure cell, right? We've made a lot of different versions. This is a 6.3 millimeter version for the squid magnetometer. This is a large angle X-ray cell that is being made by Easy Lab, but be very careful to make certain that when you give them a design that they hold to that design and don't make it simpler, because then the way it works doesn't work. These are the plastic cells, and here's the small plastic cell that we were using for the YBCO measurements. And this is a rotator made out of the same plastic, so you can do oriented work in pulse magnets or in resistive magnets. I got to get going here. People are asking about volumes and pressures. This is from Thomas Meyer. You should look up that paper if you want to get some good info. And these are the cells that the UIC group uses and the folks at HPCAT use to do the superhydride work. It's Maubel cell. These are the cells that I designed. Here's the piston, here's the body, here's an assembled cell for this superhydride work. And these are the various bits and pieces that go with it. This Russian spring and anti-rotation screw, and then the nut. Okay, and here's, again, is the plastic cell. Now, I said it's only 3 parts, right? But I threw away all the other stuff, the load mechanism and everything else, so that I could make it really small. Okay, this is just a schematic of that cell for our cell for doing the superhydride work with the Russian spring and such. Okay, it's reasonably small. We made it smaller so we could do squid measurements and that type of thing. And then Adam's already mentioned, putting these gaskets together with these cubic boron nitride inserts. And here is not our electric, or is it ours? It possibly is ours. One of the loads that we tried, not a beautiful thing, right? And then just to point out to you that when you're working with cells and samples this small, you really have to be careful of the amount of current you put into your sample, because 1, you've got contact resistance, and 2, you've got a sample that's pretty gosh darn small. But Tony Helm was really adamant that he needed just a little bit more current to see quantum oscillations in the pulse magnet, and that is the result, right? It just fried everything. Luckily, he had made 3 devices, and we loaded 3, and all 3 loaded successfully. So we just grabbed another one and went. But yeah, be careful of your experimental conditions. I don't have time to talk about that, but pulse magnets have one disadvantage. If you have put metal into them, they induce currents, and that heats up your sample, right? And that's why we came up with this idea of this plastic diamond amble cell. For the superhydrides, we're going to try to use plastic cells, but that means our QLIS have to be crazy small because the plastic isn't that strong. But the nickel chrome aluminum that we use for our diamond amble cells has a resistance of 4% IAC, 4% conductivity of copper. Even at low temperatures, it's magnetically clean, all that good kind of stuff. And you don't see a whole lot of heating when you're a pulse magnet, especially at the temperatures where we were. So. All right, don't have time to talk about that either, because I got 5 minutes, I got to roll. This is TDO versus PDO. PDO measurements for quantum oscillations are where you have the detector at the top of the probe. TDO, we put it all the way at the bottom, 2 inches from the field center. You can see a massive advantage. And this is 20 inches away, and we get another 100 times bump when we move to within 2 inches, okay? A really important thing is have fun in the lab, right? And also work with people that are crazy passionate, because you just feed off each other. And I'm certain you're at that point too, where you found the people that with whom you can have good discussions and that aren't critical of your crazy ideas and actually will help you try your crazy ideas, which will fail miserably 95% of the time, but that 5% that work, boom, you are just golden, right? And you need people that aren't going to laugh at you, right? You need the folks that step up and say, hey, I'm happy to help you with that. I have an idea. Yeah, right? That's Audrey. And she's the one who actually loaded for one of these experiments at Dresden 27 diamond anvil cells and failed 26 of them, right? We got results in that run, right? It was one of the worst runs we ever had, but we had some glorious data once that cell started to grow, right? William, we all have nicknames. William's nickname is Squirrel because William, he sees something and he's just on it. And then all of a sudden there's something flashy over here in the corner of his eye and boom, he's on that too, right? And he will just work himself to death. And then eventually you will find him in the control room with his face planted on his notebook and he's not good for a day, right? He literally will just fall asleep on you. But he's an incredible scientist. So on to the nickel hydrides. The sulfur hydrides, nickelates. This is Audrey and Mukhtar, who is just a saint. He taught her how to do all of the loading for the superhydrides. And this is our sample, our very ugly load, right? This is our lanthanum that's spewed off to the side. These are the 8 electrodes that we have fibbed on here. Tony is fibbed on. We luckily had contact with 6 of the electrodes. So we could not only do a 4-contact measurement, we could do permutations of that and show that we had, whatever we had, it was there at multiple spots. Okay? Blow up of it, and I blow that up just to show you where we're, on the next slide, where we heat it, right? So we go through, Audrey had instructions to heat, or Mukhtar, this was during the pandemic, Mukhtar got sick, he had to leave, we didn't know whether he had COVID or not, but Yue Meng said, you're out of here, right? And he came to me and said, okay, don't let her pulse more than 3 times in one spot before she moves to the next spot because something weird happens, right? And I went out to the area where she was doing the laser heating and she was seeing all these great flashes and I'm like, totally cool. And I totally forgot about what Mukhtar told me to do. And she hit it 4 or 5 times, right? And then moved over to the next spot, boom, 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 boom. You can see here, our crucible, this region here, is crazy inhomogeneous growth. It is not what Valentin has, right? We have temporal instabilities, right? We're going up to 1,200 degrees Kelvin and down to room temperature in milliseconds of time, right? And then, and then spatially, you have the same issue, right? Center of the beam, boom, you got 1,200, you hope. You know, at that point, the detector wasn't working correctly, so we saw flashes and we went with the flash. But within 30 microns, you're back down to room temperature as well. I talked about the various permutations here, and then I'll show X-ray. You can see this shows, these are essentially walking away, and you can see here's essentially where she hit it with one spot and how the stoichiometer, or how the X-ray spectra is changing. Here's another spot, here's the third spot. Here are the initial results. Not beautiful, but we see a transition here. It's reproducible, and then if we cool down at a slower rate, you can see it much more cleanly. There is nothing that is in the range of where you should see something for lanthanum H10. And to verify that we can see superconductivity with the system, we were able to go into, we had a null cell, B003, and that is the data here in the blue. And you can see these transitions here, which are due to lanthanum at various pressures, non-hydrostatic conditions, and also the platinum hydride that is synthesized in this growth. And we can see the same thing, or the same transition in B002, which was the material that made the superconducting transition here. And just to verify that they were superconducting transitions, we used applied field to shift. And I'll leave it there. It all started to get crazy when we tried to go. I said, hey, let's go up into the normal state so that we can get R versus T. Very suspect, by the way. If you do pressure measurements and you try to do R versus T measurements, be aware that your cell, when it cools down, changes pressure. And so your R versus T, if you try to fit to some model, is incorrect, right? Because you are going to, as you cool down, you're going through a family of pressures very smoothly, but you're changing your pressure. Okay? But what we have is that initial result here, right? And then when we tried to go up into the normal state, instead the gosh darn transition started to push out, right? And what we believe we have is a catalytic reaction at the electrodes that the platinum is assisting, or the fib platinum is assisting, in enhancing the growth and incorporating, we're not certain what at this point, more material, or converting more of the material, and I don't think I've got this last slide. What we, obviously people want us to reproduce. We finally were able to do that with D007, a different cell design. So here's B007. We shortened it, made it smaller so that we can do measurements in the PPMS, and then we made it crazy small, right? And this is a cell that we're trying to work with now, small enough to fit into a PPMS system, and we can also stick it into a pulse magnet. It only weighs 1.1 grams, and it doesn't heat up a whole lot, which is pretty nice, right? And we see in D007 at 172 GPa, B002, which was the initial finding, was at 175 GPa. With laser heating, ammonium boron is the hydrogen source, lanthanum, and here's that growth. Sample is dead smack in the middle of the electrodes, right? And we see the transition again. So we were pretty stoked, and at this point, moving forward. I don't want to show the X-ray data. I'll show that on Friday, and my time's run out anyway. So I'll take questions.
Okay, first question.
How many of those plastic decks do you have left?
We break a lot of plastic decks. Yeah, but the cool thing is, machining is to the point now where CNC machining, the guy can set it up, and you can make a lot of them. They hate you when you ask them to make a lot of them. But our last run was 30 cells, and the issue is that it's plastic, and if you don't machine it just right, it has all sorts of imperfections in it, and it leads to notch impurity or defects, and the cells snap at the worst point. But the highest we've had it, I think, is a 1 point or 11 point something GPa, right? So, and that's with big ambles. That was with I think it was 400 micron ambles. Oh, sorry, there is one thing I have to show you. This is cool. Stuff on safety, important. Please, if you want to look. An offspring of the plastic cell, right, is that a colleague of our, Gaston Gabarino, who's at ESRF, said, I bet you could actually blow X-rays through that. So you've got essentially a crystal at pressure on a post, and you can do 360-degree crystallography. And he was right. Right? So we took the cell recently in September 2022, Chongyong Park at HP Cat. I love his enthusiasm, right? Good guy. This is looking sideways through the diamond cell, through the cell, right? Here you can see the impression of the diamond's empty cell. Here's with the magnesium oxide in the cell, and at 20 GPa, right, in a plastic cell, and crappy data, but it's the first data that came off. So here now, and the reason I bring this up is for us, for the superhydrides, where we know we have diffusion going on, and we know we have grain growth issues. This is a really cool way that we might be able to study that, and for crystal growers, a cool thing too. Okay, sorry. Any others?
Questions? Yep.
I guess I have a follow-up. So you said they don't make that plastic anymore, is that correct?
Correct.
So you just have pallets of blocks of this plastic, which
This is all knowledge of any source of plastic.
Okay, understood.
But if you wanted some, I probably could find some. Yeah, and I've sent it here and there and everywhere. So Adam and I were talking with one of the students, right? The high pressure community is really gracious about sharing stuff, right? Not only information, but stuff. Ruby, they sell you enough Ruby that you could, I was saying, it's at least 10 lifetimes of a scientist and all of the students I'll ever work with. And we're happy to give you some plastic, the same thing. Stishov, one of the Russian researchers in high pressure, one of the gods, right? He had access to this nickel chrome aluminum, and people couldn't get it in the States, but he would bring it in as a spindle on his luggage, right? And I have one of those pieces, and I refuse to use it to make anything out of it because there's just too much good history and how it got to me, right? The guy is just really good. And high pressure community will just give you like gasket material. There's no reason to buy rolls of this stuff. You only need that much and you're good to go for a long, long time. Yeah, bother us. We're happy to send it. Yeah.
I wanted to ask about metallic hydrogen. So the calculations, if I recall this correctly, started out at a reasonable low pressure where you should solidify and make hydrogen metallic. But it doesn't seem like we've gotten there yet. Has the theory gotten better to predict the pressure whether it should happen?
Yeah, so Neil Ashcroft, bless his heart, he died a couple of years ago, but he actually saw a result and he was stoked. But he always said when we come to the next Gordon conference and nobody had a result on metallic hydrogen, you know, every year it was just people busted their butts and didn't have anything. They had data, but it just didn't look, you know, it was suspect. And that's suspect. It just it wasn't solid, right? And he said, I never said it was 250 GPa. I said it's density. You need to worry about the density. So it's obviously you need to go up in density, which means you need to go up to higher pressure. Experimentalists would go back, and Arametz and Paul Debert and others would jack the pressure up. And again, they wouldn't see it. That went on for, I don't know, how many, did you go to the Gordon conference, Bianca, when that was going on? I think it was over a course of 10 years that Neil kept on telling people, it's just a little bit higher, you know, go back to the lab. And then he realized, you know, this is a painful situation, and that's when he proposed the superhydrides in 2004. However, recently Paul Debert has this, Bianca, have you read his paper? I think it's pretty solid, right? It's optical, and people are always suspect of optical measurements with hydrogen because hydrogen, you know, diffuses into stones and reacts with your gaskets and does all sorts of crazy stuff. Paul is a crazy careful experimentalist, and it looks pretty solid, right? Aramis has some reasonably good stuff going on, and Bill Nellis has some shock data that looks really clean. So I think it's there. It's right around 450 GPa. It requires the toroid stones, which are fibbed, right? So fib again comes to play into the high pressure community. So I think we've got it. Not we. I think they've got it. So the question is, what are the other probes that we can use to convince the general scientific population that it's real and it is metallic hydrogen? And that's going to take a while. And unfortunately, Paul is retiring, but he's going to a smaller facility than CEA. So, yeah.
And it's always this fun topic to discuss in class.
Oh yeah, right? Yeah. Well, it's like the superhydrides, right? I mean, let's face it, people think you're on drugs, and I'm not. But it's, you know, and when carbonaceous sulfur hydride came out, I would bet any person that is in high pressure other than that group said, whoa, right? You can't dope in a small amount of carbon and get this huge pump, and it can't be stable, right? And when they came up, you know, and then when that finally got rejected as it should, or retracted as it should have been, because it never should have been accepted in the first place, they came up with lutetium hydride, and nature accepted that. And that will be the part of the discussion on Thursday, but that's ridiculous. At that point, it says the reviewers are not doing a good job, because one, a superconductor shouldn't be read, right? That's just bogus. And two, if you look at their data, all of their data falls from many cells where they have only a 1 in 3 success rate, right? And they have impurities that supposedly change TC. They do multiple measurements, techniques, right? Susceptibility, transport, I forgot what the others were, right? All of the data falls on this beautiful curve, right? Without error bars. When I looked at that, I just said, I've been in high pressure long enough to know that my error bars are, you know, they're solid, but they're big, right? Pressure's off, TC, susceptibility measurements and resistivity measurements of a superconductor must be at different temperatures. It is just physics, and they weren't. So something was wrong there, right? So I almost believe metallic hydrogen more than I believe superhydride at this point, right? It's just, Paul did some really solid work.
So I hate to cut you off, but I think we better get lunch going. So thank you.
I agree.
And we'll continue the discussion Thursday. So lunch is now, let's try to come back at about 1:15.
So how does the neutron look like in this